Hello, my dear students and the rest of the learners. Welcome to this presentation in which we are going to discuss on the topic file management in operating systems. This is part 1 of a 6-part series of presentations in this topic. The title of this topic is Introduction to File Management and File System. My name is MemJM, or you can simply call me ML Swap. In this presentation, we are therefore going to look at the meaning and the importance of file management, the file management system, a file system, under which we shall look at file naming, file structure, file types, file attributes, and lastly, we shall look on file operations. Let's commence by looking at the meaning and the importance of file management. All computer applications need to store and retrieve information. When a process is running, it can store information within its address space. The storage capacity is restricted to the size of the virtual address space. For some applications, this may be enough, whereas for others, it is not. A second problem with keeping information within the address space is that when a process terminates, that information is lost. For many applications, for example, for databases, the information must be retained for weeks, months, or even forever. Therefore, having this information vanish when the process is using it is unacceptable. Furthermore, it must not go away when a computer crash kills the process. A third problem is that it is frequently necessary for multiple processes to access either parts of the information or the whole information at the same time. If we have an online telephone directory, for example, stored inside the address space of a single process, only that process can access it. The way to solve this problem is to make the information itself independent of any one process. Therefore, we have 3 essential requirements for long-term information storage. Number 1, it must be possible to store a very large amount of information. Number 2, the information must survive the termination of the process that is using it. Number 3, multiple processes must be able to access the information concurrently. In addition, a few questions quickly arise, such as, number 1, how do you find information? Number 2, how do you keep one user from reading another user's data? Number 3 is, how do you know which blocks of information are free? This problem is solved by the operating system using an abstract that is called a file. Therefore, In order to ensure that the computer system is convenient to use, the operating system provides a uniform logical view of information storage. The operating system does this by abstracting the computer from the physical properties of its storage devices in order to define a logical storage unit that is called the file. A file is therefore a named storage location of related information that is a sequence of similar logical records that is recorded on secondary storage, given a single name and treated as a single entity. Files are logical units of information that is created by processes. Therefore, computers store information in form of files on various storage media, such as magnetic disks, magnetic tapes, and optical disks. Files are mapped by the operating system onto physical devices. These storage devices are usually non-volatile, so the contents are persistent through power failures and system reboots. From a user's perspective, a file is the smallest allotment of logical secondary storage. That is, data cannot be written to secondary storage unless they are within a file. Commonly, files represent the programs, both the source and object forms, as well as data. A disk would usually contain thousands or even millions of them, each one independent of the others. Files are used to model the disk instead of modeling the random access memory. Processes can read existing files and create new ones if need be. The information stored in files must be persistent, that is, not be affected by process creation and the process termination. A file should only disappear when its contents owner explicitly removes it. Therefore, files are managed by the operating system. The information in a file is defined by its creator. Many different types of information may be stored in a file source: programs, object programs, executable programs, numeric data, text, payroll records, graphic images, sound recordings, and so on. The file is created as a single entity by users and applications and may be referred by their name. Files have unique file names and may be created and deleted. Restrictions on access control as the following are therefore the main desirable properties of files. Number one is long-term existence. Files are stored on disk or other secondary storage and do not disappear when a user logs off. Number two is shareable between processes. Files have names and can have associated access permissions that permit controlled sharing. Number three is structure. Files can be organized into hierarchical or more complex structure to reflect the relationships among files usually apply at the file level. Let us now look at file management system, sometimes abbreviated as FMS. A file management system is that set of system software that provides services to users and applications related to the use of files. It has limited capabilities and is designed to manage individual or group files, such as special office documents and records. It may display report details like owner, creation date, state of completion, and similar features useful in an office environment. Typically, the only way that a user or application may access files is through the file management system. This relieves the user or programmer of the necessity of developing special purpose software for each application and provide the system with a means of controlling its most important asset. A file management system should not be confused with a file system which manages all types of data and files in an operating system, or a database management system, DMS or DBMS, which has a relational database capabilities and includes a programming language for further data manipulation. This is because a file management system's tracking component is key to the creation and management of this system, where documents containing various stages of processing are shared and interchanged on an ongoing basis. The file management system may contain features like, number one, assigning queued document numbers for processing. Number two, owner and the process mapping in order to track various stages of processing. Number three is report generation. Number four is notes. Number five, status. A file manager is therefore a computer program that provides a user interface to manage files and folders. The file manager creates the illusion that there are files and folders being stored in computer memory. The following are therefore the key responsibilities of a file manager. Number one is keeping track of where files are stored. Number two is determining how the files are stored. Number three is following system operation or following operating systems file allocation policies. Number four is using available storage space efficiently for files. Number five is creating a record or a log of all file usage. Number six is allocating a file to a user if it is free and if they are permitted to access that file. Number six or number seven is deallocating files when a user has finished with them or with it. The file manager allocates a file by reading it from the hard disk and loading it into memory while updating its record of who is using what file. The file manager deallocates a file by updating the file tables and rewriting the file if changed to the hard disk. Any process waiting to access the file will be notified. The increased simplicity of the file systems provided by modern operating systems has enabled a concentration on efficiency, security, and constrained access and robustness. The file manager administers the file system by, number one, storing the information on a device. Number two is mapping the block storage to a logical view. Number three is allocating and deallocating the storage. Number four is providing directories. In addition, the operating systems provide a layer of system-level software using system calls in order to provide services relating to the provision of files. This obviates the need for each application program to manage its own disk allocation and access. As a kernel-level responsibility, the file management system again provides a central role in resource or buffer allocation and the process scheduling. From the viewpoint of the operating system kernel itself, the file management system has a number of goals. Number one is to support the storage, searching, and modification of user data. Number two is to guarantee the correctness and integrity of the data. Number three is to optimize both the overall throughput from the operating system's global view and response time from the user's view. Number four is to provide transparent access to many different device types, such as hard disks, CD-ROMs, and floppy disks. Number five is to provide a standardized set of I/O interface routines, perhaps ameliorating the concepts of file, device, and network access. The following are the main objectives of a file management system. Number one, to guarantee the extent possible that the data in the file are valid. Number two is to provide I/O support for a variety of types of storage devices. Number three is to minimize or eliminate the potential for lost or destroyed data. Number four is to provide a standardized set of I/O interface routines. Number five is to provide I/O support for multiple users in the case of multiple user systems. Number six is easy to use and update. The minimalist approach in the interface and automated installation process makes it hassle-free for users. Number 7 is to meet the data management needs and the requirements of the user. Number 8 is to optimize performance through effective and efficient organization. Number 9 is files can be quickly rolled back to previous versions as required, as all versions are maintained. A further critical requirement in a multitasking multi-user system is that the file management system meet users' requirements in the presence of different users. Therefore, subject to appropriate permissions, a file management system should be able to provide the following important minimal requirements. Number 1 is that each user should be able to restructure the user's files in a form that is appropriate to the problem. Number 2 is that each user should be able to move data between files. Number 3, each user should be able to back up and recover the user's files in case of damage. Number 4, the recording of a primary owner of each file for access controls and accounting. Number 5, each file should be accessed by at least one symbolic name. Number 6, each user should be able to create, delete, read, and modify files. Number 7, users should have constrained access to the files of others. Number 8, a file's owner should be able to modify the types of access that may be performed by others. Number 9, a facility to copy or back up files to identical or different forms of media. Number 10 is a secure logging and notification system if inappropriate access is attempted or achieved. The following are the many functions of file management. Number 1 is to identify and locate a selected file. Number 2 is to use a directory to describe the location of all files plus their attributes. Number 3 is to describe user access control on shared system. Number 4 is blocking for access to files. Number 5 is to allocate the files to free blocks. Number 6 is to manage free storage for available blocks. Therefore, the operating system is responsible for the following activities in connection with file management. Number 1 is file creation and deletion. Number 2 is directory creation and deletion. Number 3 is support of primitives for manipulating files and directories. Number 4 is mapping files onto secondary storage. Number 5 is file backup on a stable or non-volatile storage media. Let us now look at what we call the file system in operating systems. The part of the operating system that deals with the file naming, file structure, file implementation, file access, file storage, and file protection is referred to as the file system. File system is the software which empowers users and applications to organize and manage their files. From the user's standpoint, the most important aspect of a file system is how it appears. That is, what constitutes a file, how files are named and protected, what operations are allowed on files, and so on. The details of whether linked lists or bitmaps are used to keep track of free storage and how many sectors there are in a logical disk block are of no interest, although they are of great importance to the designers of the file system. For most users, the file system is the most visible aspect of an operating system. It provides the mechanism for online storage of and access to both the data and the programs of the operating system and all the users of the computer system. The file system consists of two distinct parts. That is, a collection of files, each storing related data, and two, a directory structure which organizes and provides information about all the files in the system. The file systems live on devices. The structure of a file management system consists of the following components from the bottom up. That is what we call a file system architecture. Number one is the device drivers. These communicate directly with I/O hardware. The device drivers commence I/O requests and receive asynchronous notification of their completion via the DMA. My dear students and the rest of the learners, for you to be able to gain a detailed, deep, and a clear understanding about the I/O hardware, I/O software, and other aspects in relation to I/O management, kindly listen to the series of videos and presentations under the topic Device I/O Management that are already posted in my YouTube channel by the name MLSwap ICT, and you will be able to gain in-depth knowledge even about the device drivers. Number two is the basic file system. It exchanges fixed-sized pieces or blocks of data with the device drivers, buffers those blocks in main memory, and maps blocks to their physical location. Number three is the I/O supervisor. It manages the choice of device, its scheduling and status, and allocates I/O buffers to processes. The logical I/O layer is the other part. It maps I/O requests to blocks and maintains ownership and access information about the files. A file system is used to control how data is stored and retrieved. Without a file system, information placed in a storage medium would be one large body of data with no way to tell where one piece of information stops and where the next piece of information begins. By separating the data into pieces and giving each piece a name, the information is easily isolated and identified. Taking its name from the way paper-based information systems are named, each group of data is called a file. The structure and logical rules used to manage the groups of information and their names is called a file system. There are many different kinds of file systems. Each one has different structure and logic, properties of speed, flexibility, security, size, and more. Some file systems have been designed to be used for specific applications. The file systems can be used on numerous different types of storage devices that use different kinds of media. The most common storage device in use today is a hard disk drive. The other kinds of media that are used include flash memory, magnetic tapes, and optical disks. In some cases, such as with TMPFS, the computer's main memory, that is random access memory that we abbreviate as RAM, is used to create a temporary file system for short-term use. Some file systems are used on local data storage devices, while others provide file access via a network protocol. For example, NFS, SMB, or 9P clients. Some file systems are visual, meaning that the supplied files, also called visual files, are computed on request. For example, PROCFS, or are merely a mapping into a different file system that is used as a backing store. The file system manages access to both the contents of files and the metadata about those files. It is responsible for arranging storage space, reliability, efficiency, and tuning with regard to the physical storage medium are all important design considerations. File system types can be classified into disk or tape file systems, network file systems, and special purpose file systems. The following are therefore the main types of file systems. Number one is what we call disk file systems. A disk file system takes advantages of the ability of disk storage media to randomly address data in a short amount of time. Additional considerations include the speed of accessing data following that initially requested and the anticipation that the following data may also be required. This permits multiple users or processes access to various data on the disk without regard to the sequential location of the data. Number two is what we call the flash file systems. A flash file system considers the special abilities, the performance, and restrictions of flash memory devices. Frequently, a disk file system can use a flash memory device as the underlying storage media, but it is much better to use a file system, specifically one which is designed for a flash device. Number 3 is tape file systems. A tape file system is a file system and tape format that is designed to store files on a tape in a self-describing form. The International Business Machines, that we abbreviate as IBM, has developed a file system for tape, which is called the linear tape file system. The IBM implementation of this file system has been released as the open source IBM linear tape file system or single drive edition, that is linear tape file system single drive edition product LTFS-SDE. The linear tape file system uses a separate partition on the tape to record the index metadata, thereby avoiding the problems that are associated with scattering directory entries across the entire tape. Number 2 is database file systems. In addition to hierarchical structured management, files are identified by their characteristics, such as the type of file, the topic, the author, or similar rich metadata. Number 3 is transactional file systems. Transactional processing or transaction processing introduces the isolation guarantee, which states that operations within a transaction are hidden from other threads on the system until the transaction commits, and that interfering operations of the system will be properly serialized with the transaction. Transactions also provide the atomicity guarantee, ensuring that operations inside of a transaction are either all committed or the transaction can be aborted and the system discards all of its partial results. This means that if there is a crash or power failure after recovery, the stored state will be consistent. Either the software will be completely installed or the failed installation will be completely rolled back, but an unusable partial install will not be left on the system. Ensuring consistency across multiple file system operations is difficult, if not impossible, without file system transactions. Number 4 is network file systems. A network file system is a file system that acts as a client for a remote file access protocol, providing access to files on a server. Programs using local interfaces can transparently create, manage, and access hierarchical directories and files in remote network connected computers. Then we have what we call the shared disk file systems. A shared disk file system is one in which a number of machines, usually servers, all have access to the same external disk subsystem. The file system arbitrates access to that subsystem preventing write condition or collisions. Then we have special file systems. A special file system presents non-file elements of an operating system as files so that they can be acted on using the file system APIs. This is most commonly done in Unix-like operating systems, but devices are given file names in some non-Unix-like operating systems as well. Then we have what we call the device file systems. A device file system represents I/O devices and serial devices as files, which are called device files. In non-Unix-like operating systems and other operating systems influenced by it, where the full file name or path name of a file can include a device prefix, devices other than those concerning or containing the file systems are referred to by a device prefix specifying the device without anything following it. Then we have flat file systems. In a flat file system, there are no subdirectories because directory entries for all files are stored in a single directory. When a floppy disk media was first available, this type of file system was adequate due to the relatively small amount of data space that was available. Then we have virtual file system. This file system makes all the files on all the devices appear to exist in a single hierarchy. This means that in those systems that make use of it, there is one root directory and every file existing on the system is located under it somewhere. To gain access to files on another device, the operating system must first be informed where in the directory tree those files should appear. This process is called mounting a file system. For example, to access the files on a compact disk read-only memory, one must tell the operating system to take the file system from this CD-ROM and make it appear under a certain directory. The directory given to the operating system is called the mounting point. The following are the main aspects of file systems. Number one is file naming. Number two, file structure. Number three, file types. Number four, file attributes. And number five, file operations. Let us commence by looking on file naming. Files are an abstraction mechanism. They provide a way to store information on the disk and read it back later. This must be done in such a way as to shield the user from the details of how and where the information is stored and how the disks actually work. Therefore, the most important characteristic of any abstraction mechanism is the way the objects being managed are named. A file is named for the convenience of its human users and is referred to by its name. A name is usually a string of characters. For example, meme.doc. meme.doc is a file name and document file name which is composed of 5 characters. Double E, E. That is meme.doc. That is a file name. A file name is used to identify a storage location in the file system. Most file systems have restrictions on the length of file names. So file naming vary somewhat from system to system. Many file names or many file systems support file names as long as 255 characters, but all current operating systems allow strings of 1 to 8 letters as legal file names. In some file systems, file names are not case sensitive, that is, uppercase and lowercase letters. Uppercase means capital letters, while lowercase means the small letters. While in others, file names are case sensitive. Most modern file systems allow file names to contain a wide range of characters from the Unicode character set. However, they may have restrictions on the use of certain special characters, disallowing them with file names. Those characters might be used to indicate a device type, directory prefix, file path separator, or file type. When a file is named, it becomes independent of the process, the user, and even the system that created it. For instance, one user might create the file by the name example.c, and another user might edit that file by specifying its name. The file's owner might write the file to a floppy disk, send it in an email, or copy it across a network, and it could still be called example.c on the destination system. In any computer system, whenever a process creates any file, it gives a name to that file. And whenever the process terminates or stops running, then the file still exists, or in other words, you can say that the file continues to exist and can also be accessed by some other processes just by using the name of the file. The rule for file naming varies from system to system, but all the current operating systems allow strings as file names. Almost every operating system supports two-part file names. These two parts of the file names are specified or separated by a period, which we call a dot. The two parts are file name and a file extension. The file extension generally indicates something about the file. For example, meme.doc, myfile.back, myfile.hlp, myfile.txt. When a user double-clicks on a file system, the program assigned to its file extension is launched and given the name of the file as a parameter. For example, double-clicking on the file by the name file.doc starts Microsoft Word with file.doc as the initial file to edit. This is because Microsoft Word or Microsoft Office Word is a program which is used for creating documents, and documents have what we call a .doc extension. And for that reason, that is why the file.doc will open using Microsoft Word once you double click on it, meaning that it was created using Microsoft Word program. The following is a list of the typical file extensions and their meanings. File.doc. .doc stands for or indicates that file is a document file. File.txt is a text file. So .txt indicates a text file. .back indicates that file is a backup file. .gif represents graphical interface format image. .html indicates that this file is a World Wide Web hypertext markup language documents. File.jpg indicates that it is a still picture encoded with the JPEG standard. .mp3 indicates that this is a file for music encoded in MPEG Layer 3 audio format. .mpg indicates that it is a movie encoded with the MPEG standard. .pdf indicates that this is a portable document file. It is in what we call a portable document file format. .txt indicates that this is a general text file. .zip indicates that this is a compressed archive file. Let us now look at what we call the file structure. A file has a certain defined structure according to its type. When operating system defines different file structures, it also contains the code to support these file structures. A file structure should be according to a required format that the operating system can understand. Therefore, files must conform to a required structure that is understood by the operating system. For example, the operating system requires that an executable file have a specific structure so that it can determine where in memory to load the file and what the location of the file and what the location of the first instruction is. Some operating systems extend this idea into a set of system-supported file structures with sets of special operations for manipulating files with those structures. This point brings us to one of the disadvantages of having the operating system support multiple file structures. That is, the resulting size of the operating system is cumbersome. If the operating system defines 5 different file structures, it needs to contain the code to support these file structures. In addition, it may be necessary to define every file as one of the file types supported by the operating system. When new applications require information structured in ways not supported by the operating system, severe problems may result. For example, if a system supports 2 types of files, the text files and executable binary files, if we, as the users, want to define an encrypted file to protect the contents from being read by unauthorized people, we may find neither file type to be appropriate. As a result, we may have to circumvent or misuse the operating system's file type mechanism or abandon our encryption scheme. Some operating systems impose and support a minimum number of file structures. The following are therefore the main types of file structures that are supported by the operating systems. Number one is what we call an unstructured sequence of bytes. The operating system does not know or care about what is in the file. All that it sees are bytes. Any meaning on the content of the file must be interpreted by the user programs. Both Unix and MS-DOS use this approach. Having the operating system regard the files as nothing more than byte sequences provides the maximum flexibility. User programs can put anything they want in their files and name them in any way that is convenient. The operating system does not help, but it also does not get in the way. Number two is what we call fixed length records. In this structure, a file is a sequence of fixed length records, each with some internal structure. Central to the idea of a file being a sequence of records is the idea that the read operation returns one record and on write operation overwrites or appends one record. An example of an operating system that viewed the files as a sequence of fixed length records was the CP/M. It used a 128 character record. Number three is a tree of variable records. In this organization, a file consists of trees of records, not necessarily of the same length, each containing a key field in a fixed position in the record. The tree is sorted on the key field in order to allow for rapid searching for a particular key. The basic operation here is not to get the next record, although that is also possible, but it is to get the record with a specific key. New records can be added to the file with the operating system and not the user deciding where to place them. This type of file is widely used on the large mainframe computers that are still used in some commercial data processing. A file has various kinds of structure. Some of them can be, number one, simple record structure with lines of fixed or variable lengths. Number two is complex structures like formatted document or loadable load files. Number three is no definite structure like sequence of ones and bytes amongst the others. Four terms are in common use when discussing files. That is what we call the traditional file system concepts. These are, number one, a field. A field is the basic element of data. An individual field contains a single value, such as an employee's last name and date, or the value of a sensor reading. It is characterized by its length and data type. For example, the ASCII string or decimal. Depending on the file design, fields may be fixed length or variable length. In the latter case, The field often consists of 2 or 3 subfields. That is, the actual value to be stored, the name of the field, and in some cases, the length of the field. In other cases of variable length fields, the length of the field is indicated by the use of special demarcation symbols between fields. Number 2 is a record. A record is a collection of related fields that can be treated as a unit by some application programs. For example, an employee record would contain such fields as name, social security number, job classification, the date of hire, and so on. Again, depending on design, records may be of fixed length or variable length. A record will be of variable length if some of its fields are of variable length or if the number of fields may vary. In the latter case, each field is usually accompanied by a field name. In either case, the entire record usually includes a length field. Number 3 is a file. This is a collection of similar records. The file is treated as a single entity by users and applications and may be referenced by name. Files have file names and may be created and deleted. Access control restrictions usually apply at the file level. That is, in a shared system, users and the programs are granted or denied access to entire files. In some more sophisticated systems, such controls are enforced at the record or even the field level. Some file systems are structured only in terms of fields, not records. In that case, a file is a collection of fields. A file system architecture consists of 2 or 3 layers. Sometimes the layers are explicitly separated, and sometimes the functions are combined. These layers are: number 1, the logical file system. This is responsible for interaction with the user application. It provides the application program interface API for file operations and passes the requested operation to the layer below it for processing. The logical file system manages open file table entries and per process file descriptors. This layer provides file access, directory operations, and security as well as protection. Number 2 is the visual file system. This is an optional layer. This interface allows support for multiple concurrent instances of physical file systems, each of which is called a file system implementation. Number 3 is the physical file system. This layer is concerned with the physical operation of the storage device, for example, a disk. It processes physical blocks being read or written. It handles buffering and memory management and is responsible for the physical placement of blocks in specific locations on the storage media. The physical file system interacts with the device drivers or with the channel in order to drive the storage device. Number 2, let's look at file types. This refers to the ability of the operating system to distinguish different types of files. Many operating systems support many types of files. Many operating systems, particularly Those used in personal computers tend to use file type information within a name. Most PC-based operating systems associate file systems or file types with the specific applications that generate them. For instance, a database generating program will leave explicit information with a file descriptor that it has generated or that it has been generated by a certain database program. A file descriptor is kept within the file structure and is often used by the file system software to help operating system provide file management services. For a user, the extension in the name of a file helps to identify the file type. When a user has a very large number of files, it is very helpful to know the type of a file from its name extensions. In general, there are 3 ways of indicating the type of a file. Number 1, the operating system may record the type of a file in metadata that is stored separately from the file but associated with it. Number 2, the type of a file may be indicated by part of its contents, such as a header made up of the first few bytes of the file. Number 3, the type of a file may be indicated by its name. For example, results.pdf. Operating systems support several types of files, which are, number 1, regular, simple, or ordinary files. These are the files that contain user information and may belong to any type of application. They may have text, databases, or executable program. The user can apply various operations on such files like add, modify, delete, or even remove the entire file. Generally, regular files are either ASCII files or binary files. ASCII files. ASCII files are files that are basically, or which basically consist of lines of text that need not be of the same size, but are determined by the carriage return or line feed character. The big plus point or advantage of ASCII files is that they can be displayed and printed as is, and they can also be edited using any text editor, such as Notepad, WordPad, Notepad Plus, amongst the others. Then we have what we call the binary files. These files on listing on the printer gives some random junk. Generally, binary files have some internal structure that is only known to the programs that use them. Technically, binary files are just a sequence of bytes. The operating system will only execute a file if it has the proper format. Number 2, we have what we call the directory files. Directory files are files that contain a list of file names and other information related to these files. They are the system files that are used to maintain the structure of the file system. Number 3, we have what we call the FIFO files. These are files that are used by the system to maintain some order during the processing or during the process of executing processes by the processor. When a user makes a request for services from the system, these requests are arranged in these files, and then they are all executed based on their order of arrival. Number 4, we have what we call special or device files. These are the files which are not created by the user and are generally and are necessary to run a system. They include all the system files. These files represent physical devices like disks, terminals, printers, networks, tape drives, amongst the others. These files are of two types. Number one, we have what we call the character special files. Data is handled character by character, as in the case of terminals or printers. Basically, character special files are related to the I/O and are used to model simple input-output devices such as printers, networks, amongst others. Then we have what we call the block special files. The block special files are data or are files in which data is handled in blocks, as in the case of disks and tapes. Basically, block special files are used to model the disks. When we design a file system in Int or indeed an entire operating system, we always consider whether the operating system should recognize and support file types. If an operating system recognizes the type of a file, it can then operate on the file in reasonable ways. A common technique for implementing file types is to include the type as part of the file name. The name is split into two parts, a name and an extension that is usually separated by a period character. In this way, the user and the operating system can tell from the name alone what the type of file is. Number 4, let's look at file attributes. This is an extra information that the operating system associates with each file in addition to the name of a file. This extra information is called metadata. Therefore, the attribute fields provides the operating system with the necessary information pertaining to a file. The list of the attributes varies from one system to another. The following is therefore a list of some of the major file attributes, even though not all may be present in a single operating system. Number 1 is protection. It determines who can access the file and in what way. Access control information determines who can do reading, writing, executing, and so on. Number 2 is password. Password is needed to access the file. In some systems, the user must present a password to access a file, and in this case, the password must be one of the attributes. Number 3 is creator. It indicates the identity of the person who created the file. Number 4 is owner. It shows the current owner of the file. Number 5 is name. The symbolic file name is the only information that is kept in human readable form. Number 6 is identifier. This unique tag, which is usually a number, identifies the file within the file system. It is the non-human readable name of the file. Number 7 is type. This information is needed for systems that support different types of files. Number 8 is location. This information is a pointer to a device and to the location of the file on that device. Number 9 is read-only flag. This determines whether a file can be read from or written into. Number 10 is hidden flag. This determines whether a file will be displayed or not. Hidden files do not appear in listings of all the files. Number 11 is system flag. It indicates whether a file is a normal or a system file. Number 12 is archive flag. It indicates whether a file has been backed up or if it needs to be backed up. Therefore, the archive flag is a bit that keeps track of whether the file has been backed up recently. The backup program clears it, and the operating system sets it whenever a file is changed. In this way, the backup program can tell which files need backing up. Number 13 is the ASCII binary flag. ASCII or binary flag. It indicates whether a file is an ASCII file or a binary file. Number 14 is what we call the random access flag. It indicates whether a file requires sequential or random access only. Number 15 is temporary flag. It indicates whether a file is normal or requires to be deleted or process exit. I repeat, the temporary flag indicates whether a file is normal or whether it requires to be deleted or the process exit. The temporary flag allows a file to be marked for automatic deletion when the process that created it terminates. Number 16 is lock flags. This indicates whether a file is unlocked or locked. Number 17 is what we call the record length. It indicates the number of bytes in a record. Number 18 is called the key position. It indicates the offset of the key within each record. Number 19 is key length. It indicates the number of bytes in the key field. Number 20 is the creation time. It indicates the date and the time when the file was created. Number 21 is the time of last access. It shows the date and the time when the file was last accessed. Number 22 is the time of last change. It shows the date and the time when the file was last changed. Number 23 is the current size. It indicates the number of bytes in the file. It tells how big the file is at the present. Number 24 is what we call the maximum size. It indicates the number of bytes the file may grow to. Some old mainframe operating systems require the maximum size to be specified when the file is created in order to let the operating system reserve the maximum amount of storage in advance. Then we have the creation time. It indicates the date and the time the file was created. The time of last access shows the date and time the file was last accessed. We have also looked at the time of last change, the current size, the maximum size. So the first four attributes that we have looked at related to the file's protection, and they tell who may access it and who may not. The flags are bits or short fields that control or enable some specific property. Just as a reminder, the following are the first four attributes that we purposes of file protection. And these are the protection attribute, the password attribute, the creator attribute, and the owner attribute. So, it is also important to remember or to note that the record length, the key possession, and the key length fields are only present in files whose records can be looked up using a key. They provide the information that is required to find the keys. The various types keep track of when the file was created, most recently accessed, and most recently modified. These are useful for a variety of purposes. For example, a source file that has been modified after the creation of the corresponding object file needs to be recompiled. The data indicated in the form of attributes can be used for protection, security, and usage monitoring, and all this information about all files is kept in the directory structure, which also resides on secondary storage. Typically, a directory entry consists of the file's name and its unique identifier. The identifier in turn locates the other file attributes. It may take more than a kilobyte to record this information for each file. In a system with many files, the size of the directory itself may be megabytes. Because directories, like files, must be non-volatile, they must be stored on the device and brought into memory piecemeal as needed. Let's now look at file operations. A file, just as I have said before, is an abstract data type. To define a file property, we need to consider the operations that can be performed on files. Files exist to store information and allow it to be retrieved later. Any file system provides not only a means to store data organized as files, but also a collection of functions that can be performed on those files. Different systems provide different operations to allow for storage and retrieval. These operations are performed through the use of various system calls. The following are therefore the main file operations, which we also refer to as the common system calls that relate to the files. Number one is create. It is used to define a new file and position it within the structure of files. It announces that a new file is coming and sets some of its attributes. The new file created is usually without any data. Two steps are necessary to create a file. Number one, space in the file system must be found for the file. And number two, an entry for the new file must be made in the directory. Number two is delete. It removes a file from the file structure and destroys it. It is, therefore, performed to erase a file that is no longer needed so as to free up disk space. To delete a file, we search the directory for the named file. Having found the associated directory entry, we release all file space so that it can be reused by other files and erase the directory entry. Number three is open. Before using a file, a process must open it. The purpose of the open call is to allow the system to fetch the attributes and the list of disk addresses into main memory for rapid access on later calls. The open operation takes a file name and searches the directory, copying the directory entry into the open file table. The open call can also accept access mode information, which includes create, read only, read write, append only, and so on. This mode is checked against the file's permissions. If the request mode is allowed, the file is opened for the process. The open system call typically returns a pointer to the entry in the open file table. This pointer, not the actual file name, is used in all the I/O operations, avoiding any further searching and simplifying the system call interface. Number 4 is close operation. When the file is no longer being actively used, it is closed by the process and the operating system removes its entry from the open file table. When all the accesses are finished, the attributes and disk addresses are no longer needed, so the file should be closed in order to free up internal table space. Many systems encourage this by imposing a maximum number of open files on the processes. A disk is written in blocks, and closing a file forces writing of the file's last block, even though that block may not be entirely full yet. Number 5 is read operation. It is performed just to read the data that are stored in the required file. Usually, the bytes come from the current possession. The caller must specify how much data are needed and must also provide a buffer to put them in. To read from a file, we use a system call that specifies the name of the file and where in memory the next block of the file should be put. Again, the directory is searched for the associated entry, and the system needs to keep a read pointer to the location in the file where the next read is to take place. Once the read has taken place, the read pointer is updated. Because a process is usually either reading from or writing into a file, the current operation location can be kept as a per process current file position pointer. Number 6 is write operation. It is used to update a file either by adding new data that expands the size of the file or by changing the values of existing data items in the file. This operation is performed on the file, usually at the current possession. If the current possession is the end of the file size increases. If the current possession is in the middle of the file, the existing data are overwritten and lost forever. To write a file, we make a system call specifying both the name of the file and the information to be written to the file. Given the name of the file, the system searches the directory in order to find the file's location. The system must keep a write pointer to the location in the file where the next write is to take place. The write pointer must then be updated whenever a write occurs. Number 7 is append. This operation is the same as the file write operation, except that the file append operation only adds the data at the end of the file. This call is a restricted form of write operation. Number 8 is seek operation. This operation specifies from where to take the data. It repositions the file pointer to a specific place in the file. The directory is searched for the appropriate entry, and the current file possession pointer is repositioned to a given key or to a given value. After this call has completed, the data can be read from or written to that possession. Repositioning within a file need not involve any actual I/O. Number 9 is get attributes. This operation is performed by the processes when they need to read the file attributes to do their required work. Number 11 is set attributes. Or number 10 is set attributes. This operation is used to set some of the attributes, that is user settable attributes, after the file has already been created. This is because some of the attributes are user settable and can be changed after the file has been created. Number 11 is rename. This operation is used to change the name of the existing file. This is because it frequently happens that a user needs to change the name of an existing file. Number 11 or number 12 is truncating a file. The user may want to erase the contents of a file, but keep its attributes. Rather than forcing the user to delete the file and then recreate it, this function allows or except for file length, but tells the file to be reset to a length 0. Number 12 is lock. Locking a file or a part of a file prevents multiples. For an airline reservation system, for instance, locking the data while making a reservation prevents reservation of a seat for 2 different travelers. Most of the file operations mentioned involve searching the directory for the entry associated with the named file. To avoid this constant searching, many systems require that an open system call be made before a file is first used actively. The operating system keeps a small table which is called the open file table, containing information about all open files. When a file operation is requested, the file is specified via an index into the table, and therefore, in this case, no searching is required. We have come to the end of part 1 of these presentations on the file management topic in operating systems. You can now proceed to listen and watch the part 2 video in this series, which is by the title File Management Techniques. Congratulations, therefore, for viewing and listening to this video on the introduction to file management and file systems, which is part 1 of 6 in file management topic. You can listen to the other parts of file management topic, as well as other videos in the field of computers or ICT from MLSwap ICT YouTube channel. In addition, you can access free life skills, motivational, and inspirational resources from MLSwap Motivation YouTube channel. You can tap on subscribe button for each of these 2 channels for ease of access to the channel's content if you have not already subscribed. If you have any questions, suggestions, or even any other type of comments concerning this video and any other video that is posted under either MLSwap ICT or MLSwap Motivation YouTube channels, kindly feel free to write it to us through our email mlswap@gmail.com. Thank you very much for listening to me, and be blessed.